you for inviting me. So this is joint work with Ana Laura Trujillo Negrete. And I'm very happy about this work because it took us a lot of effort to get it done. And it's problems that I've been thinking for quite some years now. And so it's as follows. Suppose you have a graph G, and you place K tokens on the vertices of G, and you create a new graph whose vertices are the possible configurations of these K tokens. And please, everybody, feel free to interrupt me whenever you want. It's okay. So the rule is that I don't allow more than one token per vertex. And the rule is that I go from one configuration to another by taking a token and sliding it along an edge to an unoccupied vertex. So for example, if this is my graph G, then this is its token graph of 2 tokens. Okay? So
sorry. So the tokens are not labeled?
The tokens are not labeled. Okay. Thank you. Yes, the tokens are unlabeled. Yeah. So here I have all possible configurations of 2 tokens, and if I take, say, this token here and slide it along this edge, then I will end up in this token configuration, right? So this is the token graph of the 2 token graph of G. Now this is, I started with the cycle C4, and then I got the complete bipartite graph K24. Okay, so formally we can define it as follows. Its vertices of the K token graph are all the subsets of size K of vertices, where A is adjacent to B whenever its symmetric difference is an edge of G. Right? That's precisely the definition. We were very happy when we defined token graphs and we named them as such. But then many years later, we found out that actually they have been defined before. They have been defined independently at least 4 times under different names. So Jones defined them in its PhD thesis in '88. Then Alavi, Betzad, Erdos, Alik in '91. And then Terry Rudolph defined it. He was interested in the isomorphism problem. And then we defined it in 2012. Sorry, give me one minute. Okay, thank you. So the Johnson graph is actually the K token graph of the complete graph, right? Its vertices are all the subsets of size K, and 2 are adjacent whenever the symmetric difference has size 2. Okay. Now we are interested in the following question. Suppose I give you the token graph of a graph. Can you reconstruct the original graph? Okay. Now this makes sense, or it's interesting when K is not either 1 or the number of vertices -1, because clearly the 1 token graph of G is isomorphic to G, and the n-1 token of G is isomorphic to G. So, I mean, yeah, if you don't tell me K, then I can always assume that K is equals to 1, I give you a graph. But so we're interested in when K is not either 1 nor n-1, okay? And the conjecture that we have is that if you have 2 token graphs that are isomorphic, then the underlying graphs have to be isomorphic. That will mean that you can reconstruct. That means that it's uniquely determined by the underlying graph. And so we are working on this direction, trying to prove that conjecture. And interestingly enough, this is related, unsurprisingly, to the automorphisms of the graphs. So take an automorphism of G. An automorphism is just a bijective function from the vertices of G to itself that preserves the adjacency relationship. And now clearly an automorphism of G induces an automorphism of the token graph. And the way to do it is you just apply it vertex-wise. So recall that the vertices of the token graph are subsets of k vertices, right, of G. So you apply the automorphism on each vertex and you obtain a new subset of k vertices. And that is an automorphism of the token graph. It can be shown that actually, if you map in this way automorphisms of G to automorphism of the token graph, that you have an injective group or homomorphism. So different automorphisms of G go to different automorphisms of the token graph. So that implies that in particular, the automorphism group of G is always a subgroup of the automorphism group of its token graph. And it can be a proper subgroup. There are instances when it's actually the automorphism group of the token graph is larger. So when we first encountered this phenomenon, it was very mysterious because it seems very counterintuitive. Like, where are these new symmetries coming from? Like why? It sort of doesn't quite make sense, because sometimes it is the same group, and sometimes it's bigger, and it can be quite bigger. In this a small example, for example, the automorphism group of the fourth cycle is the diedric group of 8 elements, and the automorphism group of the token graph, recall that it's a K24, is C2 times the symmetric group of order 4. So it has 48 elements. So it can be quite larger. And now we have an answer to that. And but before that, let me.
I think you're muted.
I was muted. Yeah. I think it's okay now, right? Yeah.
Yes. Now we hear you.
Okay. Again. So when K equals n over 2, when K equals n over 2, the complement map is an automorphism of the token graph. Okay. So suppose that.
I think you muted yourself again. There seems to be some button that.
Yeah, no, it was me. I got a call. Sorry about this. I have to take care of something. Thanks. So yes, when you have exactly half the number of vertices as tokens, then the complement will map sets of size k to sets of size k. And it turns out that that actually is also an automorphism of the token graph. And this new automorphism is never induced by an automorphism of G, okay? And that implies, in particular, that the Cartesian product of the automorphism of G times C2, it's a subgroup of the automorphism group of the token graph. Because the complement by itself is the identity, and it commutes with every element with every automorphism of the token graph. It's easy. So these things are easy to prove. But we always have that. When K equals 2, then n over 2, we have that the automorphism group times Z2 is a subgroup of the automorphism group of the token graph. Now, so just keep that in mind. Keep that in mind that there is this thing that the automorphism group of the token of G sometimes is a subgroup of the automorphism group of the K token graph. Now, we need to lay out some work to talk about what does it mean to reconstruct a graph, right? And suppose I give you a graph F. Now I call a pair G phi a reconstruction whenever phi is an isomorphism from F to the K token graph of G. So that's a K reconstruction or reconstruction of S of F as the K-token graph of G. That is, if you think about it, what I'm doing is I'm taking every vertex of F and I'm labeling as a vertex of the token graph. I'm saying, oh, this is a set of these K vertices of G, right? And since it's an isomorphism, it's what we want, right? That's reconstructing a graph. That's saying, okay, I'm going to look at F as a token graph, as the K token graph of G. Okay, so we say that F is K token reconstructible if for every 2 token reconstructions G and G prime, we have the underlying graphs are isomorphic. So that if you reconstruct it as the K token graph of G and as the K token graph of G prime, then you have to have essentially the same graph. Okay, that means that it's uniquely determined, that it's a K token reconstructible. But then we thought about the following. Suppose that I reconstruct the graph and then you also reconstruct the graph with as a K token graph, but our reconstructions are not the same. Now, suppose that we use the same underlying graph, but for some vertices we don't have the same labeling. But then I look at your reconstruction and say, you know what? It's essentially the same because yours is only my reconstruction, but applying an automorphism, right? So if I reconstruct the graph and label the vertices and then apply an automorphism of G on all these vertices, then obtain a new reconstruction, right? So that lets us to define when F of K of G is uniquely reconstructible as the K token graph of G is that whenever 2 reconstructions, right, there is an automorphism of G such that your isomorphism is just a composition of mine with an automorphism of G. Okay, so here it should say G, not G prime, right? So recall that phi is an isomorphism from Fk of G to itself. It's an automorphism now of Fk of G, and phi prime is as well. Okay, and now we say that it's uniquely reconstructible whenever you have 2 such reconstructions, you have that they are related in this way. So one is the composition of the other by an automorphism of G. Okay, that's what it means to be uniquely reconstructible. So you reconstruct it as a token graph of G in essentially a unique way. That means that it's essentially modulo an automorphism of G. Okay. So a first result in this direction is that this notion of uniquely reconstructible is intimately related to the automorphism group of the token graph. So we have equality in the previous inequalities that I showed you. Whenever the token graph is uniquely reconstructible as the K token graph of G. So whenever you can reconstruct it in only one way, it means that there are no new symmetries on the token graph. So that was our first one of the first surprises. Like, okay, these 2 things are related. The new symmetries that appear, if they appear in the token graph, are because of different ways of reconstructing the graph. Okay. So now what else were we able to prove is the following. So C4 is the cycle of length 4, and this is the diamond. Okay, it's just a cycle with a diagonal, a 4 cycle with a diagonal, and we were able to prove that if G is a connected, I missed here. Sorry, I should have said here connected. If G is a C4 diamond-free connected graph, that means that it doesn't contain C4 or a diamond as induced subgraph. It can contain them as subgraph, but not as induced subgraph. Then, given only F, a graph isomorphic to Fk of G, we can compute in polynomial time a graph isomorphic to G. So there is we found a polynomial time algorithm to give you a graph isomorphic to the underlying G. Moreover, we were able to prove that it's unique, that it's reconstructible. And
can I ask
we
a
were able,
question?
yeah, sure, please.
Sorry. Polynomial in what? In the size of G or in the size of f of G? Because
In the size of f of G, of fk
okay,
of G.
because
Yes.
fk on G can be exponential, I guess, if
Right,
k is
right.
O of n, right?
Yes,
Okay.
but your input is a graph f.
Oh,
it's
okay.
not G.
I see. Yeah,
Yeah,
that makes sense. All right, thanks.
yeah. We also were able to prove that the token graph in this case is uniquely reconstructible as the k token graph of G, which is pretty nice because now we know that whenever G is a connected C4 diamond free connected graph, we know what the token, the automorphism group of the token graph will be. So the proof is quite long and it took us quite some time. It was quite hard to do it. But I want to give you a brief sketch of the proof. So the idea is as follows. Is first you have to consider how are C4s generated in the token graph, okay? It turns out that by case analysis, you can prove that there are exactly 4 ways in which you can generate a 4 cycle in the token graph. So either you have a 4 cycle and you have one token moving along this 4 cycle like this, like suppose I have this 4 cycle here in G, and I move one token along this 4 cycle, that will generate me a 4 cycle in G, okay? Now, or I can have 2 disjoint edges and move one token in each independently. That will also generate a 4 cycle. Or I could have something like this, right? Where I can move these tokens in this way. So this guy moves here, right? And then to go from here to here, you move it that way, but then you move this one the other direction. Okay? So, and then you have this other way, but this is just three tokens and one non-token. You can think of the white vertex as a token. It's just the complement of this guy. Okay, so if you notice here, if we disallow induced 4 cycles or diamonds, then we are forbidding these guys here, and we are only left with this way of producing induced 4 cycles in G. So that's pretty powerful because whenever we see a 4 cycle, in the token graph, we know that the opposing edges have to be generated by moving a token in the same edge. Okay, so we can generalize this relationship by something that we call ladders, and a ladder is just the Cartesian product of an edge and a path. And if you think about it, well, this edge in the token graph is generated by moving a token along this edge, but then so is this edge. So for example, you have this situation. So this vertex here in the token graph, suppose that is this token configuration, and then you move to this guy, then you move this edge, right? And then you move this vertex to here, and then you are moving on this path, and so on. So we can compute what we call the ladder relationship in polynomial time, which means that 2 edges are in the same ladder if there is a ladder containing them as rungs of the ladder. So that's easy to do. You just produce the ladders and see whenever 2 of these are connected by a ladder. And once you do that, you know that these 2 edges are generated by moving the same token along the same edge. Unfortunately, it's not an if and only if. It could be the case that 2 edges are generated by moving a token along the same edge, but they are not connected via ladder. Okay, so you have some partial information, but not quite. Anyway, so yes, even if these 2 guys are far away, we know that they are produced by moving a token along the same edge. Now, what else? Now consider a vertex of the token graph, okay, and consider its neighbors or its incident edges to this token configuration in G. By that, I mean the edges that have exactly one endpoint in a vertex of A. So what I painted in red here is my token configuration. And then what I'm painted in blue is these edges that I call E of A that have exactly one token, one endpoint in one of the vertices of A. And well, I can find out who these guys are because they are just the neighbors, the edges incident to the neighbors. And using the ladder relationship, I can recover the line graph of these edges. Okay? Because the only thing that I care about for the line graph is whether these edges are incident to a same vertex. And if they are not incident to a same vertex, then there has to be a for cycle containing them, right? It's an if and only if. And once you have the line graph of this graph, you can reconstruct, in this case, the underlying, the graph induced by these edges. Okay, so we are reconstructing very locally small parts of the graph. But that was just what we needed to as a seed to reconstruct the whole of G, the whole of Fk of G. So yes, from the ladder relationship, we can reconstruct the line graph of G of A. And from this line graph, we can reconstruct the underlying graph. And we choose A with the largest matching, okay? In this graph that I painted green. What is the largest matching is if you think about it, is the largest set of at most K independent edges in G, right? Whenever you find a set of at most of say R, where R is the largest set of independent edges at most K, place one token in each of them and place the other tokens whenever you want. And this matching will be a matching on my graph G of A. Okay. So we iterate over all vertices of the token graph. We generate this local subgraphs. For each, we compute a maximum cardinality matching, and we take the one with the largest matching. Okay. Now we know that these edges are generated by moving a token along one edge, these joined edges. So they must generate a cube of 2 to the R vertices in the token graph. We can generate this cube in polynomial time because these relationships give us where to move. And once we have this cube, we say, okay, we have reconstructed a small part of the graph as a product of K22s, right? So let me call this K22s H1 up to HR. Now, what I'm going to do is I'm going to grow these small parts into larger parts. I'm going to start reconstructing them. And that's tedious, but it's doable. And what you do is you start with, say, H1, which currently is an edge. And suppose it has a neighbor, right? One of these vertices has a neighbor. So you move the token to this neighbor, and you can you can determine whether it was indeed by moving a token from here to another vertex. And the way to do that is you use the ladder relationships. So when you move this token from here to here, you have to be able to still move these tokens, right? So if I move this vertex from here to here, the new vertex has to have edges incident in the same ladders as these two guys here, because I am still able to move these guys. So I move, and I move over all my other guys to see if they still have a neighbor in those ladder relationships. And if it's good, then we are happy because it's indeed a movement on a edge incident to what I wanted to reconstruct, what I call G1. Okay. Now, some caveat of this is that it could be the case that actually it is not the case maybe that a token from my K2 moves outside, but it could be the case that a token that was outside moves inside. Okay, like this. Maybe this was my configuration and a vertex here, and a token here move to the inside. But in any case, I can start adding new vertices to my HI. And in the end, what I end up with is a maximal graph H that is a Cartesian product of H1 to HR, where each HI is the token graph of some subgraph GI of G. Okay. Now I have F, I have some subgraph H, and I have a partition of the vertices of G into connected graph GI. Okay. And such that every H is the token graph of these GIs. Okay. And I have a mapping. Every vertex in H, I'm labeling as the token graph of some subgraph of GIs, as the Cartesian product of the token graph of GIs. Okay. So what was crucial is the fact that we started with the largest matching. That has some implications of what we are doing here. Because suppose that HI is formed by moving more than one token, let's say 2 tokens, okay? It cannot be the case that the underlying graph GI has 2 disjoint edges, because if that were the case, then I can move these 2 edges and produce a larger matching. That's what I started with. Okay, so whenever your HI, you manage to show that is generated by moving 2 tokens, then its underlying graph cannot have 2 disjoint edges. That implies that there is only a small number of ways in which each HI can be generated. So it is either, the GI is either an edge and a token moving on this edge, or GI is a triangle and you have either 1 or 2 tokens moving along this triangle, or this is a bit tricky, it's a graph GI isomorphic to the token graph of a star, but you only have 1 token moving along this graph, okay? Or you have the token graph of a star and you have more than 1 token. So this guy can produce an H with disjoint edges. Or you have a star and only 1 token, or you have a graph that is neither one of the previous ones, an underlying graph, but you only have 1 token moving on this graph. 1 or of n-1 tokens. You always have the complement. Either you have 1 token or all of them but 1. Okay. So these guys are easy to realize that they are either to determine. And then we can recognize a token graph of stars in polynomial times. It's tedious, but you can do it. So that takes care of this guy. And then we only have to take care of these guys. But then with some effort, we can use what we already know to distinguish when we have the token graph of a star with more than 1 token, or a graph isomorphic to the token graph of a star with 1 token. Once you do that, you have pretty much reconstructed a large part of G. We only need to reconstruct the edges that go between the GIs. And it takes a lot of effort, but you can do it. After you do that, then you are happy because you have reconstructed a graph isomorphic to G. And now the harder part that this requires a lot of more work is to show that this reconstruction of H, you can extend it to a reconstruction of all of F in a unique way. So once you reconstruct this small part, all the other parts are determined, and that implies that it's uniquely reconstructible as the token graph of G. So yeah, that's for connected graphs. And we were quite happy about this. I think it's a strong result. Now, what can we say about this connected graph? Well, Ana Laura in her master's thesis found an example where I think is very interesting example, that suppose you have a different number of tokens. You have 3 and 2 tokens, right? So here is an example of G1. Here is an example of G2. And it turns out that the 3 token graph of G1 is isomorphic to the 2 token graph of G2. And these two guys are not isomorphic. What we show in this particular example, what we show in our result is that even if you just tell me, here is a graph F, okay, and it's not the 1 token graph, neither the n-1 token graph of G, then I can reconstruct G. This is no longer true if the graph is not connected. Even if it's C4 and diamond-free graph, that no longer holds. What we could show in this case is that if you give me the number of tokens, you say, okay, here are 2 graphs disconnected that are C4 and diamond-free graph. They are disconnected, but they are generated by moving the same number of tokens on the underlying graph. Then we can show that the underlying graphs have to be isomorphic. However, we cannot do this in polynomial time. And our bottleneck in this case is the isomorphism problem. And yeah, so this is all on my side.
All right, thank you very much. Are there any questions? So I have one, which is again kind of about the complexity maybe. So if I just give you a graph and an integer k, and I ask, is this graph that I give you the k token graph of some other graph?
Mm-hmm.
Can you give me an answer?
Well, it depends. I can test in polynomial time whether the underlying graph has its C4 or diamond-free graph.
Sure. Yes.
But that's not trivial. I mean, I can even if you give me the graph, I can determine whether your underlying graph has a C4
the underlying
or
graph. Aha, okay.
Yes. So if it passes that first test, then in polynomial time I can tell you yes it is, and here is the graph, or no it's not the graph. If the algorithm fails in some part, then it is not a token graph of a graph. Or I could realize, you know what, it might have C4, so diamond, so I don't know how to do it.
Okay. So the general problem could be hard.
Yes, my intuition is that it could be algorithmically quite hard. And the reason is that we have an upcoming paper where we study how large can the, or give examples rather of instances where the automorphism group of Fk of G grows exponentially, even considering the size of the graph. And in that case, my intuition is that you have many ways of reconstructing it. So somehow we were able to do it in polynomial time because the reconstruction is unique modulo automorphism. So once we fix the H, there's only one way to reconstruct the whole graph. But if it's not were the case that is uniquely reconstructible, then you have too many options and maybe you cannot do it in polynomial time. Or at least I cannot do it in polynomial time. But yeah. And it's interesting because this is related to the isomorphism problem, and who knows if that can be done in polynomial time.
Are there any conditions that you can say that some given graph is definitely not a k-token graph? I mean, for example, do you know that k-token graphs have to have some connectivity conditions or? Yes,
we know a lot about the token graph. So for example, we know its lower bounds on its connectivity. We know its number of edges related to the number of vertices. So yes, there are some tests that you can make and discard some instances. Yeah.
Okay. Nice. Are there any other questions? Does not seem to be the case. So thank you again, Ruy.